Oops, sorry, first technical problem on my end. Forgot to unmute myself. Thank you for joining me this afternoon in getting a brief introduction into EBRAINS and what we're doing in the big data space. So allow me to share my screen. Okay. And I think with that, we are live. Good. My name is Martin Telefant. I work at EBRAINS ASBL, and over the next couple of minutes, I'll give you an introduction of what EBRAINS and HPP is doing in the space of big data. After the presentation, I'll be open to questions, and also, of course, I'll be able to redirect you to people that are more knowledgeable about certain aspects of my presentation than myself. So before we jump directly into big data, I'd like to take a step back and give you a bit of a perspective of what big data means in the life sciences. So big data in life sciences is usually connected with the emergence of new technology, or the adoption or the utilization of new technology. So when you're thinking about new technology in life sciences, it's usually established technology that is used in new and creative ways. Think about, for example, information that you've seen recently on news about real-life tracking and real-time tracking of, say, fish migrations, or the increasingly detailed establishment of forest profiles, capturing the activities, the details of organisms in these vertical and horizontal columns of life. Now, sampling standardization often leads to big data. It is not really the emergence of new technology, but the standardization. Good example of that one is in the omics space, where genomics, proteomics, metabolomics, metagenomics, transcriptomics, and the likes have really led the way on being able to generate large amounts of data in really small amounts of time, and being able to process this information in a way that you don't have to wait for years for information to be decoded and useful. If you think about it, at the beginning of the Human Genome Project, the estimate of how long it would take to decode the entire human genome was around 10 years. Today, it can be done in a day. Also, the cost of a lot of this work has come down drastically in a matter of years. So a lot of times, it is not really the introduction of new technology, it's the adoption and really the use of the technology that leads to big data. Now, why gather big data? This is one of the questions that has plagued the life sciences for a while, because traditionally life sciences have really been hypothesis driven, in the sense that you have a experimental question, you have a limited number of subjects that you're sending into a situation where your hypothesis is confirmed or rejected. But the decreasing cost of data generation makes that actually an approach that is needs to be combined with discovery of new information coming out of data, large amounts of data. And since life sciences is also an area of research that is largely affected by probability rather than distinct yes or no situations, gathering a lot of data and processing a lot of data to understand what is happening and where we are in a certain spectrum of behavior is really a key. Now, the ideal situation in the life sciences and in other areas is really a happy side-by-side between theory and data. Ideally, creating situations where a crossover works out and we have new theories based on data, or data proving and disproving existing theories, or leading to new ways of thinking about entire areas.
Martin,
yep.
This is Jaakko from BDVA, your tech support here. I'm very sorry to interrupt, but I think you should maybe swap the displays on your PowerPoint. We see the back end of your presentation.
Okay. Well, let me see. Swap displays. I hope that does it.
That did it. Thank you very much. Please carry on.
Thank you. Now, when we're looking at brain data in particular, and big brain data, or big data about the brain, there's really two aspects when you look at it. One is that data of that size has been used to help us give hope to some areas where theoretically it's been possible to show that certain activities can be modeled and can be expressed, but the brain was the only machinery available to show that it can work once technology is at the level of being able to mimic it. There's a quote by Geoffrey Hines that I caught a couple of weeks ago at the Canadian Theoretical Neuroscience Conference, where he said for half a century, the brain was the only reason for believing that big neural networks that learn almost everything from data would ever work. So it is something to keep in mind that a lot of the technology currently used for processing big data is based on relative simple machinery that we've seen working for quite a long time, and that was in effect active in the brain. Now, the second aspect is, well, we'd actually like this network, this system, to keep working, because when things don't work, that's usually not good for us as human beings, but also for society as a whole. The cost of brain disorders in Europe alone in 2010 was around 800 billion euros. That is a lot of money. If you think about that, we're talking here about a relative simple structure not working. The brain is not large, but it's very complex. Now, disorders in this space can range from the cost of around 300 euros for working with a situation that gives you headaches to something around 30,000 euros a year when it comes to neuromuscular disorder, and that's where we're really talking disabilitating situations. Now, when you're thinking about the brain, there is really two things that work against you if you're trying to understand the whole system. That's what big data is often used in this space, and that is the brain is a multi-level organ. It covers a lot of different ranges with respect to scale. You're going from the micrometer scale where cells and synapses interacting, all the way up to meters where people are moving around and interacting with the environment and everything in between. Also, time scales. You're really going from a scale where you're seeing individual molecules interact with each other, we're talking picoseconds, up to things that are changing or staying the same over a matter of years or decades even. When it comes to sampling, that's another area that we don't have a single technique that allows us to sample information at all levels. On the right side of this slide, you're seeing there's a range of different sampling techniques available that capture different time and space ranges. And one aspect that is not captured here, but is also something to keep in mind, the brain is not a machine that you can leave running 24 hours a day. You can't even sample from it 24 hours a day. So capturing real-time information at a scale where you would approach something of being able to capture the entire range of activities, even within a day, is well beyond what can be currently collected. Another aspect is nobody is out there writing checks for big data in life science, and especially neuroscience. So a lot of times when we're seeing big data, it's really the result of years of work, in the sense that there's a proposal, for example. A proposal will stipulate that it'd be a good idea if we gather some data to understand a certain situation. Based on this seed data in the first line here on the right side of proposal, there might be another proposal written that then gathers more data or adds on top of that. And then in the last stage, for example, here in the last proposal on the left side, you would then finally reach something of complexity and size where you'd say that that is approaching big data. But what you can see here is that it's a process. A lot of times when you get to big data, it is based on information gathered, evaluated, tools built for it, and also insight gained from the process. Now, on top of that, a lot of times before you get to the big data stage, you're really talking about potentially people combining data, saying this is of similar type, this would show what we could do if we had, say, 50,000 records. Currently, we don't. We have 250 from over here. We have 330 from over there. We got 70 here. But you can see the value of adding more information to this to get a better feel of the landscape that this big data sample is describing. And another thing to keep in mind, even if you have big data, you're studying a complex system. So it might not be enough gathering a lot of data about one dimension if it is something that then cannot be, or only very crudely be translated to another dimension, either time or space. Compute. Now, if you're looking into the news and the literature, you will hear and see about the wonderful computing capacities of the brain, but to look at how the brain's doing things, you also need compute, and you need a lot of compute, from really image acquisition to analysis, to stitching, to feature extraction, to then building models. This is unfortunately still not something you can run on your desktop, and that's where compute, cluster, supercompute really comes in. Another aspect is really the complexity of how we're dealing with the data. The amount of data in neuroscience and life sciences often determines how you can work with it. Sometimes it's impractical to move the data. There's too much data, and it's a lot easier moving the code to where the data is. But that creates problems, for example, if you need certain compute capacities to be able to work with the data itself. So again, it's a consideration on, if you have big data, if you're planning to generate big data, where are you going to keep it? How are you going to process it? Because putting it in a truck and moving across a country, it might not be an option. That's also where rules come in. A lot of data in this space is very sensitive data. It is data gathered from humans. And that's where, depending on the context, it might not even be possible to move the data outside of the building that it was captured in. To give you an example, think about hospitals. And on top of that, privacy. We're all concerned with what can be learned from our data, not just from our healthcare providers, but also other parties that are part of this ecosystem. Now, that's where I'd like to sidestep a bit the depressing picture I painted for you here and talk about EBRAINS, because EBRAINS is trying to do something that we feel the brain research space desperately needs. And that is a infrastructure that allows researchers and healthcare providers and other people that are working and trying to uncover how the brain does its things or understand where things go wrong, that allows them to work with compute and data that, again, a lot of times are not possible to make available to them on infrastructure that they have available by their organizations. Now, EBRAINS is not coming out of nothing. It is the result of the Human Brain Project, which is an EU-fed flagship. And at the end of the Human Brain Project in 2023, the EBRAINS research infrastructure will continue to offer services that were built and tested and developed by researchers of the Human Brain Project to the research community. Now, what sets EBRAINS apart from other initiatives in this space is that it makes really state-of-the-art data, simulation and modeling tools, and compute infrastructure and resources available to the community. Now, EBRAINS is a research infrastructure in the making. We are working with partners across Europe to establish and expand on this pan-European scientific synergies and expertise sharing that the Human Brain Project started in 2013. We are the research infrastructure of reference when it comes to neuroscience. There is no other neuroscience research infrastructure in Europe around. But given the interconnectedness and really the limitations that we have globally on studying and understanding the brain, it is also a research infrastructure of global relevance, as not every region sees a sense in replicating work that is done somewhere else in the world. Now, there are two aspects that we'd like to highlight when it comes to EBRAINS. We are an enabler. We are enabling scaling up and development of existing things. but also initiators would like to trigger new top-down scientific projects that really require a research infrastructure and the experience in building it and maintaining it for projects that are coming and are in the process of being built. Now, EBRAINS covers largely 3 areas that are connected to the brain, and they're, in a way, if you want, different perspectives on the brain. There's neuroscience, the area of research that tries to understand how the brain works, from the single synapse all the way up to behavior. Brain medicine, which is really coming in with respect to what happens if things don't work out the way they're supposed to, or how can you avoid the onset of certain conditions by living a healthy lifestyle and doing or not doing certain things. And of course, as I described earlier, the brain is a complex system, and in that it is a treasure trove of how nature has solved problems that we're only starting to hit now with our technology. So brain-inspired technology is also something that comes out of the data and simulation and modeling tools that are available over EBRAINS, because they are a reflection of this complex system that we're studying. Now, good news, we have been recognized by the ESFRI, and we are on the ESFRI roadmap as of earlier today, which is good, because ESFRI is really a seal of excellence and approval in that its mission is to develop the scientific integration of Europe, to strengthen its international outreach, and to provide Europe with the most up-to-date research infrastructures. So we're very happy about this, we're very honored, and that means no sleep for a lot of us for the coming years. Now, a bit of perspective, there are, of course, other research infrastructures out there. There are 341 actually, research infrastructures that are connected to biological and medical sciences, 8 of which are connected to neuroscience, but all of them are single site based, and they're built around national areas of excellence. EBRAINS is different in that it is a federated research infrastructure. We are really trying to bring together the best that different areas in Europe have to offer, both technologically and topically. Now, where we are at the moment is that EBRAINS has a central hub that is located in Brussels. We have a number of national nodes that are in the formation all across Europe that are then connecting the individual expertises that are available, either based on the organizations that are part of the national hubs or facilities connected to them. And by facilities, we're really talking from scanners all the way up to compute facilities. Now, to give you a bit of an overview of where we are in time, it doesn't go back all the way to the beginning of the Human Brain Project, but you can see that we're in about the middle of the slide, a bit to the left, where EBRAINS is still very much supported by funding that goes to the Human Brain Project for developing these technologies, gathering data, testing it, reaching out to other researchers. But after the end of the Human Brain Project in 2023, we are continuing to prepare the infrastructure and to work on its first implementation, and after 25, the operations with respect to the definition of this under the ESFRI. So that was interesting and nice, but let's look at some of the things that are available on EBRAINS. So there are a number of aspects that are potentially of interest to many of you in the audience, in that, for example, one of the things that we're looking into is a combination of applications that allows clinical decision support tailored to individuals and applied at clinical trials. There are also efforts underway for multi-scale integration to identify key mechanisms that predict disease progress from novel therapeutic solutions, and of course, high-performance compute enabling high-resolution individual and extension of modeling cohorts. Because in the end, it is most likely that a lot of the insights and a lot of the applications of knowledge that we're acquiring will be translated to the real world of building more customized, more better adjusted models that mimic the brain of people that are in need to better understand how a certain disease or how a certain situation affects them. Now, the different major platforms and solutions available at the moment are based on these individual components here, and I'll highlight each one of them individually in a second. But we're talking about data and knowledge, atlases, simulation, brain-inspired technology, and medical data analytics. Now, how do you not just capture information about the brain, but how do you store it? How do you make it findable? How do you make it reusable? That has been one of the big questions, and we've worked on this for the last couple of years, really since 2013, since the beginning of the Human Brain Project. And the solution that we have available is the EBRAINS knowledge graph. Now, it is a system that allows you to not just annotate captured information, but also link it to extract features, ontologies, and also tools that are then able to further process, refine, or in various ways interact with the data in itself. Atlases are a fundamental tool really when it comes to neuroscience. Think of the effect that Google Earth had on navigation. The atlases do the same thing when it comes to the brain, only that the brain is not like the Earth or Google Earth, a thing that is mostly of interest to us when flat, but the brain is three-dimensional. A centimeter down from the cortical surface is also pretty interesting, and depending on what you're interested in, it might be more interesting than the surface itself. Now, simulation is really at the heart of helping us understand, if we understand the system we're studying, because like I said, it's not possible to capture the entire system at all levels at any point in time. So building models based on data that we have to test hypotheses that we're thinking about and that we'd like to have proven is really a fundamental tool. We can keep gathering data for the next decades to come. Models will help us understand what to do with the data and what data we're missing to better understand the system, as a lot of these dimensions that I described earlier, time and space, are interdependent and really linked with one another. Now, this is not a segue over to a new sci-fi book, but we are, as humans, interacting with space, and we're interacting with space with the bodies that we have. So our brains are very much a reflection of our ability to interact with space around us and the space interacting with us. So testing what we understand about the brain in an environment that makes sense to the brain is really something that makes sense. Now, if we're looking again at the medical situation, we're again looking at a problem of data accessibility and data processing, in the sense that this is very sensitive data. But for healthcare professionals and people working in medical informatics to get access to data, to understand the data, to understand what can be done with the data, to understand the context the data was gathered in, potentially previously analyzed or treated, is pivotal. And for that, you need a safe and secure environment that allows access and processing of data available in multiple sites. That's where, for us, the federated architecture of the medical informatics platform is a solution to this problem. Now, to take a step back from what I just showed you in these applications, when it comes to what happens next, it is really saying, well, how do you build workflows that aren't encapsulated by these applications I just showed you, but that can leverage them? So it's very basic. All of these workflows depend on data. Data, a lot of times, is not enough. You need curation. Curation can here really range on metadata tagging. It can really go down all the way to spatial alignment to make sure that, well, you've aligned your scan to a reference space where you can compare it to other data that was captured under similar or different conditions. That's where, for us, the information in the end culminates in records available over our knowledge graph that is then used by different applications to access it in its most simple form over a text-based search engine, or available in spatial locations in Atlas, which are then used as an input to tools that try to understand this data, try to process it, try to extract features, biomarkers, or build models on top of that. And that's where really resources like high performance computing or cluster computing or neuromorphic computing come in handy, because you want these activities not just to run, but run as efficient as possible. Now, what we are in the process of doing is we're working on making all of our service really building blocks for the community to build something that we couldn't imagine, we haven't imagined, but that they don't need to start from scratch, but really leverage what has been done and also the compute substrate that these applications run on top of. So each tool is moving towards becoming a tool in a toolbox that will allow people to mix and match certain functionalities and build their own ways of creating pipelines for data that they're likely to have, or they're in the process of writing proposals to get. So here's an example of one of the applications that is built on top of some of the services I've showed you previously, and that is the virtual brain workflow. If you haven't seen it, you seriously go to YouTube, check it out. It's amazing work. Now you can see some of the components in this workflow are fairly standard. I mean, we didn't invent Docker, neither Python, but we're sure happy that they're around. But we really need them to work as intended in this workflow and interface with the different applications and different services that are around for researchers then to be able to build personalized models of people that are suffering, for example, from epilepsy. Now here's an example of what big data sometimes looks like in neuroscience. This is a composite of individual slices of a human brain. You're right now flying through what is called the hippocampus. To give you a bit of a scale reference, the hippocampus is about 3 to 3.5 centimeters cubed. Your entire brain is about 1,200 centimeters cubed. So we're talking about a tiny, 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 tiny piece. But you can already see, depending on the sampling and depending on the processing, that we're already talking about quite a lot of data. And we're not even talking feature extraction yet. We're talking about stitching of images, large images, aligning them across the third axis, C here, just to be able to capture this little piece of tissue. And with this, I shut up for a bit and let you enjoy the flight. Now, to lead slowly but surely over to the question part of this session, we're of course open and eager to collaborate with people that would like to contribute to advancing brain research in Europe. Now, there are collaborations that we are pursuing and in the process of building across multiple levels at the European level through, for example, participation in Horizon Europe calls, European Innovation Council, ERC calls, but also at the national level, where we are, as I said before, in the process of establishing a network of national nodes, but also interfacing, working with innovation, science and tech initiatives and the likes, and also special programs. If you've been listening over the last couple of days, data spaces are a big thing. They're coming, they're here. They will be with us for a while. And of course, we're also interested in working with people that are thinking and developing and designing in the health data space. But we're also, of course, working with the established national and regional programs, for example, when it comes to supporting or connecting structural funds that have been allocated or in the process of being allocated to infrastructures that are supporting brain research, for example, with respect to, for example, image acquisition, standardization, for data streams and these kinds of things. Now, if you are here because you have a service yourself and you're interested in understanding how we are looking at services, we're looking at services from 4 different perspectives. There are scientific services that are largely developed by research teams that have research questions. They're able to provide a certain level of support, but it is really something where the research drives the question and not necessarily the use of the technology afterwards. They're supporting services, really foundational things, as I showed you a couple of slides ago, to make sure that there is always a Python interface to supercompute and similar things. And those are the services out of sight, but they are the things that make the machinery work. There's, of course, then the services that we consider EBRAINS services, where we're aiming to serve really large user bases. We're talking about the entire neuroscience community, for example, thousands and thousands of people, where support's available during office hours, business office hours, and your request is coming through. You don't have to find space between schedules of people that have teaching and research obligations, but they also require really a long-term commitment to make sure that they are available, and they're available at a level of support and quality that is expected by people that depend on them. And of course, we're open and in the process of talking with organizations that would like to offer commercial services to the brain research community. And that's where then we're really talking about different models, where we're talking about per user pricing of services and dedicated SLAs and user agreements, which aren't really things that are, I would say, standard in academia. Now with that, I'm at the last slide of my presentation. I'd like to thank you for your attention. I know that we're nowhere near the time allocated for this session. And with this, I think I'll take the slides off and I will look in the forum what questions you have posted there. And also briefly highlight that this is not the only chance that you have to interact with EBRAINS. We're also here in a number of other meetings. For example, we are available today between 5 and 5:30 in the matchmaking and networking session, as we are tomorrow from 12:30 to 1, and from 1 to 1:30. And we also have a booth where you can stop by and ask your questions, and where we are doing our best to connect you to people that have more answers than we have. Thank you for your attention.